Hello, my name is Dan Leonte. I'm a PhD candidate at Imperial College London, and today I'll be talking about simulation methods for trawl processes. This is joint work with my supervisor, Professor Almut Gerard. As I've already mentioned, this talk is about trawl processes, which are continuous time, stationary, and infinitely divisible processes. And these processes can describe a wide range of serial correlation patterns in data. This talk is structured as follows: introduction, a quick review of Levy processes, followed by the definition of Levy bases, and then finally the trawl simulation algorithm. Before we delve into any of that, we need two key concepts for this talk. The first one is the concept of an ambit set, ATFX, which can be thought of as the region which influences the value of a random field called an ambit field Y at a given point xt in space-time. So common examples include light cones and sound cones, but the choice of ambit set differs significantly from one setting to another and is informed by the knowledge we have about the system we are trying to model. This is one particular example of an ambit set. Modeling with ambit sets in general enforces the belief that the value of the spatiotemporal field y at coordinates xt is only influenced by a subset of the system, denoted here by ATFX, and not by the entire system. The other key concept for this talk is that of a Levy basis, which is a type of random measure which generalizes Levy processes. The example to always have in mind is that of a Poisson random measure. For the purposes of this talk, we will set ATFX to be a fixed set A translated by x in the spatial component and t in the time component. Then it is natural to define the spatiotemporal field YTFX to be the Levy basis L evaluated over the set ATFX. And further, it is easy to define just a temporal process, xt, which is obtained by fixing the spatial component of y to be 0. And in the following, we will concentrate on trawl processes, that is xt. This is an illustration of a trawl process. So in the following, we have that the ambit set is given by this curvilinear triangle, translated by, say, S1 units, S2 units, S3 units, and S4 units on the time axis. Then the values of the trawl process are given by the Levy basis evaluated over these triangles, these curvilinear triangles. Let us now introduce the concept of Levy basis, and to begin with, let us review the theory of Levy processes. We say that an RD-valued stochastic process is a Levy process if it starts at 0 with probability 1, it has stationary and independent increments, and it is continuous in probability from the right. And the continuity from the right is given by this condition here. An important consequence is that such a process has an infinitely divisible distribution. And an important theorem, which we will generalize to Levy basis, is the Levy-Hinton representation, which gives us an expression for the characteristic function of an infinitely divisible random variable. To understand this expression, we can separate the first two terms from the last term. And we can recognize the first two terms as the characteristic function of a Gaussian random variable, whereas this is a jump part and can be thought of as a compound Poisson process. Let us now introduce Wavy bases. And in the following, we will restrict to sets A, which are Borel measurable and have finite measure. This is just a technical restriction. So Wavy basis L on RD is a collection of random variables LFA satisfying the following three conditions. Additivity for any disjoint sets A and B. We have L of A union B is equal to L of A plus L of B. Independent scatteredness, in the sense that for any disjoint sets A and B, we have the random variables L of A and L of B are independent. And finally, the law of L of A is infinitely divisible. The first two conditions already hint at the fact that L can be thought of as a generalization of white noise processes to processes which no longer have, or not don't, which, to processes which don't necessarily have a Gaussian marginal. The third condition might seem a bit restrictive at first, but most distributions we use in practice have infinitely divisible, are infinitely divisible. For example, Gaussian gamma, inverse Gaussian, so on and so forth. We have the following generalization of the Levy-Hinton representation to Levy bases. The only difference being now that psi star, A star, and N depend on A, which is to be expected since we are computing the characteristic function of L of A. In the following, we make this following simplifying assumptions that psi star, A star, and N scale with the Lebesgue measure of A. This will ensure that the trawl process is stationary. So we obtain the following simplification of the Levy-Hinton representation, where this part here is the same as in the Levy-Hinton representation of a Levy process. Then we scale it by the Lebesgue measure of A. Let us understand this, this notion of Levy basis by three different examples. The first one is the example of a Gaussian Levy basis where L of A has a normal distribution. In this case, we don't have a jump component and L is just 0. The second example is that of a Poisson Levy basis where L of A has a Poisson distribution with intensity given by lambda times the Lebesgue measure of A. In this case, psi and A are 0. So we have no Gaussian component, and L is given by lambda times the Dirac delta measure at 1. L of A can follow many other laws such as gamma inverse Gaussian, normal inverse Gaussian, so on and so forth. Before we introduce the new simulation algorithm, let us discuss what previous simulation ideas used. So let us begin by trying to simulate a Poisson Levy basis. So the second example on this slide. To do so, we bound the ambit set in a rectangle. So here we would have a rectangle of height 1 and length 8. Then we sample a Poisson point process and we count how many dots are inside each of these ambit sets. This is because the Levy measure L is a constant times the Dirac delta measure at 1. In general, if the Levy measure L doesn't have such a simple expression, we have to adapt slightly the simulation algorithm. We still simulate a Poisson point process, but to determine the value of xt, instead of looking at how many points are contained inside the ambit set, we associate to each point a random sample drawn from the distribution, the Levy distribution L. And then the value of xt is given by the sum of the values associated to points which are contained in the ambit set. This poses certain technical challenges. First, if the Levy measure L cannot be normalized to a probability measure, that is, if it has infinite mass, then we have to truncate the support of L, and this results in an inexact simulation. The second problem is that simulating probability distributions with a truncated support can be a bit tedious because such distributions are usually not included in standard computer libraries. In order to address these issues, we propose the following simulation algorithm called the slice partition algorithm, where we simulate the trawl process at equidistant times s to s up to ks. The idea is to use suitable slice partitions together with the additivity and the independent scatterness of the Levy bases. So we designed the following labeling system where we count from left to right and from top to bottom. And say we want to simulate the value of the trawl process at 4s. In order to do so, we look at all the slices Sij which are contained in this trawl, in this ambit set, shown with my cursor. Then we independently simulate values for each of these slices, and then we add up all these values. We can add them up because of the Levy additivity property, and further we can simulate the values of the Levy bases over these slices independently because these slices are disjoint, hence we can apply the independent scatteredness property. So in this ambit set, we notice that we have the following slices: S41, S42, S43, S44, which are written on the bottom row here. Then we have S32, S33, S34 written here, so on and so forth. We can represent their sum as the following component-wise sum between this filter and the values simulated the matrix of values simulated from the Levy basis. So in particular here, S41 would be a random sample from the distribution of L S41. It is not hard to see that as we slide this filter to the right, we're going to obtain the value of X5s, X6s, S7s, so on and so forth. Hence, we can represent the simulation procedure of trawl processes as a convolution, which can be implemented efficiently in most computer packages via the fast Fourier transform. Thank you very much for your attention.